Episode 7. Title of the REL course is Energy Physics. In this episode 7, first we will discuss about components of tidal power plants. There are three main components of tidal power plants. One is the powerhouse, second one is the dam or barrage, that means low wall to from basin. Third one is slice waves from the basin to the sea and vice versa. The turbines, electric generator and other auxiliary equipments are the main equipments of a powerhouse. The function of dam to form a barrier between the sea and the basin or between one basin and the other in case of the multiple basins. The slice waves are used either to fill the basin during the high tide or empty the basin during the low tide. As per operational requirement, these are gate controlled devices. It is generally convenient to have the powerhouse as well as the slice waves in alignment with the dam. The design cycle may also provide for pumping between the basin and the sea in either direction. If reversible pump turbines are provided, the pumping operating can be taken over at any time by the same machine. The modern tubular turbines are so versatile that they can be used either as turbines or as pumps in either direction of flow. In addition, the tubular passages can be also used slice waves by locking the machine to a standstill. As compared to conventional plants, this, however, imposes a great number of operations in tidal power plants. For instance, the periodic opening and closing of slice waves of tidal plant are about 730 times in a year. Dam, that means barrage. Dam and barrage are synonym terms. Barrage has been suggested as a more accurate term for a tidal power scheme because it has only to withstand hits. A fraction of the structure height and stability problem are far more modest. However, the literature does not always make the distinction even though heads are small with tidal power cutoff. Tidal power barrage have to resist wave whose shock can be severe and where pressure changes side continuously. Since barrage length adds also the price tag of the plant, short barrage are preferred even if basin size may have to be smaller as a result of site choice. Up to a high height of 20 meter cost remains proportional to length as it is not changed by the need to build a dam wall to withstand high hydrostatic pressure. When the elevation exceeds 20 meter limit, cost increase faster with length. Most tidal power plants do not have heads exceeding 20 meter. The barrage needs to provide channels for the turbine in reinforced concrete. To build these channels, a temporary cofferdam is necessary, but it is now possible to build them on land, float them to the site, and sink them into place. Flatness is required for the sea bottom. Sandy bottom usually necessity pilling. There where sand or rock can bear the weight of the structure of implanted. The bottom can be prepared, the structure placed on it and then anchored. Prefabricated concrete blocks can be used as the core for large barrage and voids filled with rocks and concrete remaining holes with sand, and the entire construction then asphalted. Construction of a barrage usually will influence the tidal amplitude. Indeed, such a construction modifies the effective length and embankment or basin and its shape as well, particularly if the scheme involves supplementary spur dams. The construction influences the resonance of the bay, and most bays are less than the resonant length of the tidal wave. If the resonance is reduced, the range will decrease. If measures are taken to augment the resonance, tide amplitude may be increased. Tidal barrage requires sites where there is a sufficiently high tidal range to give a good head of water. The minimum useful range in around 3 meters. The best sites are bay and estuaries, but water can also impounded behind reservoir built between 2 points on the same shoreline. The precise design of barrage and its mode of operation depend critically on the requirement for power and a careful analysis of the economics. Next one is gates and locks. Tidal power basins have to be filled and emptied. Gates are opened regularly and frequently, but heads vary in height and on the site where they occur, which is not the case with conventional river projects. The gates must be opened and closed rapidly, and this operation should use a minimum of power. Leakage is tolerable. For gates and barrage, since we are dealing with seawater, corrosion problem or attitude. They have been very successfully solved by the cathodic protection and were not possible by paint. Gate structure can be floated by modulator units into a place, though in exciting plants vertical lift gates have been used. Technology is about ready to substitute a series of flaps that operates by water pressure. Flap gates are gates that are positioned so as to allow water into a holding basin and require no mechanical mean operation. If used, they are positioned in the case of modulator construction in the caissons. A caisson is the floating into a place. They have to build so that they will be adequate for the maximum tidal amplitude. Top hung on a gate hosting beam, a gate would transfer its hydraulic load to concrete structure. If operation is to be rapid and efficient, gate must be opened under the maximum differential head. This favors as flat as possible the tidal basin face of the sluice. The flap gates allow only in the direction of the sea to the basin. Hence, the basin level rises well above the sea level as ebb flow area is far less than flood flow area. Next one is powerhouse. Because small heads only are available, large size turbines are needed. Hence, the powerhouse is also a large structure. Both and French Soviet operating plants use the bulb type turbines. Of the propeller type with reversible blades, bulbs have horizontally shafts coupled to a single generator. The cost per installed kilowatt drops with turbine size, and perhaps larger turbines might be installed in future major tidal power plant. Next one is the bulb rule. Rand's example. The bulb type turbine is an axial flow turbine. The bulb set, resembling in appearance a small submarine, is made up of an ogive-shaped steel shield containing an alternator and Kaplan turbine. It is placed in horizontal hydraulic duct and entirely surrounded by water. A shaft provides communication with the engine room of the power plant. The set functions as a turbine and as pump and regulate the flow in both direction of flow. Tide to reservoir, that means basin, and reservoir to tide. The alternate is directly coupled to the turbine and turned in at some pressure. The turbine is cable wheel with 4 mobile blades and guide vanes. The group functioning as a turbine in the direction sends basin to the sea and furnishing power in reverse sea to the basin direction, functioning as a pump in direct sense. Next one is rim type turbines. Different types of turbines are under study. Usually mentioned are included sheave turbines, rim type turbines, or straight flow turbines, where the generator is attached peripherally on the turbine's blades, an arrangement that couples two turbines of conventional type to one generator, and hydraulic system in which up to 6 turbines are coupled to hydrostatic pumps and to drive a Pelton wheel, which in turn drives a high-speed generator. The main problem in rim type turbine, in which the rotator surrounds the turbine runner as the rim carried by the runner blade, is the seal between the stationary parts and the rotating rim. Engineers who favor straight flow generator against the bulb turbine generator point out the lower inertia characteristics of the bulb type, claiming this could be lead to problem during power system disturbance. The designers of a new type of straight flow unit put forth saving in civil works and in generation and auxiliary electrical equipment because large unit capacities than with the bulb type unit for the same head would be possible. Next one is operation methods of utilization of tidal energy. The generation of electricity from water power requires that there should be difference in level between which water flows. A number of concepts have been proposed for generating electricity by utilizing the head that can be produced by the rise and fall of the tides to operate hydraulic turbine. The power generation from tides involves flow between an artificially developed basin and the sea. However, in order to have more or less continuous generation, this basic scheme can be elaborated by having 2 or more basins. Accordingly, we can distinguish the following types of arrangement. First one is single basin arrangement, second one is double basin arrangement. Single basin scheme can generate power only intermittently, but a double basin scheme can provide power continuously or on demand, which is tremendous advantage. The drawback is that the civil works become more extensive. In the simplest double basin scheme, there must be dam between each basin and the sea, and also dam between basin containing the powerhouse. One basin is maintained always at a lower level than the other. The lower reservoir empties at the low tides and upper reservoir is filled at high tide. If the generating capacity is to be large, the reservoir must be large, which usually means that the dams will be long. Next, we will discuss about single basin arrangement. The simplest way to generate tidal power is to use a single basin with retaining dam in the following manners. In a single basin arrangement, there is only one basin interacting with the sea. The two are separated by a dam, that means barrage, and the flow between them is through sluice ways located conveniently along the dam. Potential head is provided by rise and fall of the tide water level. This is usually accomplished by blocking the mouth of a long narrow gates in the reservoir. The dam or barrage embodies a number of sluice gates and low head turbine sets. The generation of power can be achieved in a single basin arrangement either as single ebb cycle system, single tide cycle system, double cycle system and more cycle system. Single ebb cycle system. When the flood tide, that means high tide, comes in, the sluice gates are opened to permit seawater to enter the basin or reservoir, while the turbine sets are shut. The reservoir thus starts filling while its level rises, till the maximum tide level is reached. At the beginning of the ebb tide, the sluice gates are closed. Then the generation of power takes place when the sea is ebbing, that means flowing back of tide, and the water from basin flow over the turbines into the lower level sea water. Next one is single tide cycle system. In single tide cycle system, the generation is affected when the sea is at flood tide. The water of the sea is admitted into the basin over the turbines as the flood tide period is over and the sea level starts falling again. The generation is stopped. The basin is drained into the sea through the sluice waves or gates. The tide cycle requires a deeper reservoir so as to locate the sills of the sluice gates deeper, and thus the requires greater construction cost. It has been estimated that the energy produced by an ebb cycle system can be as much as 1.5 times that by a tide cycle system. The main disadvantage in both the ebb cycle as well as the tide cycle system is intermittent nature of their operation. However, since the intermissions occur at regular interval, there is a possibility of connecting another supplementary system so as the balance discontinuity. Such possibilities can regulate the output. The system can be geared as to generate power both during the ebb and flood tide with help of a single basin only. This system is known as the double cycle system. Double cycle system. As stated above, in double cycle system, the power generation is affected during the ebb as well as the flood tides. The direction of flow through the turbines during the ebb and flood tides alternates, but the machine acts a turbine for either direction of flow. In this method, the generation of power is accomplished both during emptying and filling the cycle. Both filling and emptying process take place during short period of time. The filling when the ocean is at high tide while the water is the basin is at low tide level. The emptying when the ocean is at low tide and the basin at high tide level. The flow of water in both directions is used to drive a number of reversible water turbines, each driving an electrical generator. Electric power would thus be generated during two short periods during each tidal period of 12 hours 25 minutes or once every 6 hours 12.5 minutes. Though the double cycle system has only short duration interruption in the turbine operation, yet a continuous generation of power is still not possible. Furthermore, the period of power generation coincides only occasionally with the period of peak demand. These problems are solved to some extent in the two basin scheme described. However, a fundamental drawback to all methods for generating tidal power is variability in output caused by the variation in the tidal range. Next one is double basin arrangement. It requires two separate but adjacent basins in one basin called upper basin, that means high pool. The water level is maintained above that in other, the lower basin, that means low pool. because there is always a head between upper and lower basin. Electricity can be generated continuously, although at variable rate. In this system, the turbines are located in between the two adjacent basins, while the sluice gates are, as usual, embedded in the dam across the mouths of the two gateways. At the beginning of the flood tide, the turbines are shut down. The gates of upper basin A are open and those of the lower basin B are closed. The basin A is thus filled up while the basin B remains empty. As soon as rising water level A provides sufficient difference of head between the two basins, the turbines are started. The water flow from A and B through the turbines generating power. The power generation thus continues simultaneously with the filling up the basin A. At the end of the flood tide, when A is full and the water level in its maximum, this continues until the head and water level in A and sufficient run turbines. With the next flood tide, the cycle repeats itself. With this twin basin system, a longer and more continuous period of generation per day is possible. The small gaps in the operation of such stations can be filled up by thermal power. The operation of the two basin scheme can be controlled so that there is continuous water flow from upper to lower basin. However, since the water head between the basin varies during each tidal cycle, as well as from day to day, so also does the power generated. As in the case of single basin scheme, the peak power generation does not often correspond in time with peak demand. One way of improving the situation is to use off-peak power from the tidal power generators or from an alternative system to pump water from the low basin to the high basin. An increased head would be available for tidal power generated at the time peak demand. This is very similar to pump storage system in hydroelectric power stations. Next one is estimate of energy and power in simple single basin tidal system. The expression of maximum energy can be generated during one generation period can be derived with the help of the following concept, which shows the case of the basin beginning at high tidal level emptying through the turbines to the ocean which is at low tide. That means the identical energy will generate in reverse process. During the emptying process, the differential work done by the water is equal to its potential energy at the time. Considering a tidal range capital R and intermediate head at a given time, the amount of work is calculated considering a small head dh for a intermediate head small h as discussed in the concept. We can write dW is equal to dm into g into h. Then dm becomes minus rho capital A dh, and also dW is equal to minus rho capital A dh gh. W is known as work done by water, small g is gravitational constant, small m is mass flowing through the turbine, small h is head in meter, rho is water density kilogram per meter cube, capital A is basin surface area, consider constant meter cube. The actual power generated by real tidal system would be less than the average theoretical power obtained by the above expression. Due to frictional losses and conversion efficiencies of turbines and electric generators, the actual power generator may be about 25 to 30% of the theoretical power. The work is proportional to square of the tidal range. The power is the rate of doing work. Thank you.